So this is my final project. It consists of mostly file loaded models, which I'm browsing through the DirectX app header file are each located here. So most of these consist of a graphic object, a model, texture, and a world matrix. Some have multiple textures for models that consist of multiple meshes. And then there's some objects that are based on the primitive models that I will show you later in my code. So here's the scene. So as you can see, it's kind of a medieval fantasy scene. I've put some tree models around. There's a home model table. Some of these materials are reflective. So for instance, this cauldron has a high specular property, so it reflects light quite nicely. And I chose to make some of these wooden textures and the tree textures have no specular reflection, so that they look a bit more matte. I added a few point lights into the scene, so there's the light coming from the candle on the table. That's a point light. There's a light under this cauldron here, lighting up that spider, and there's a purple point light in this kind of magical portal demo here with all of my primitive shapes floating around it. So these are all generated models: the pyramid, sphere, and two both wrapped and face textured cubes. And all of these reflect light. It's kind of hard to see that, but these are all reflecting light properly. Yep. I also put this kind of giant flying dragon there, which happens to do a great job of reflecting the directional light that I've put into the scene. And it kind of demonstrates the fog effect as well. As it flies overhead, it kind of disappears into the fog. So I'll try to show that. Yeah. Okay, so I'll walk through some of the features of my API that allowed this scene to happen. So I showed you the header file. I'll now walk through kind of the main setup in the CPP file. So first I have my shaders initiated. So I have a texture shader, which I've assigned a fog vector value that is a sample to kind of match the background of the skybox. So I set those parameters manually, but you could just as easily use the default values, which would turn this fog feature off completely. The first two are actually the number of point and spotlights in the scene. So right now I have 0 spotlights and 3 point lights, but I've commented out the fog settings and just using the default values. You see the fog effect is no longer there. So these two numbers correspond to the number of point and spotlights. So I have 3 point lights in the scene, and when I set those, I can set the number that corresponds to which light I'm assigning. So right now I have index 0, 1, and 2 point lights, each with their own settings. And since I have a color shader for my sphere model, I assign the same values so that the light settings match, and the color light shader has the exact same arguments as the shader texture light, so I can only set the number of lights, and it will just assume I don't want any fog in the scene. So then I go through and initialize all my models. Some of these have multiple textures, and that is because I have the capability to load models with multiple meshes and assign those separate materials. So if I jump to my graphic object texture light file just for a second, you'll see I have methods for either setting the material for every mesh in the object, or just assigning it based on the mesh number that I'm interested in. And this is determined on construction based on the mesh count that's taken from the model object. So all of these follow the same trend, and then I have my, actually starting here, I have my primitives. So these are loaded from the model pack that's in the model tools. So let me jump to that. So I have two functions for creating boxes. So the first one has a repeated texture UV mapping. So all these faces are independent of each other and share UV values, so that when you apply the texture, it just gets repeated over each of the six faces. And then for the wrapped cube, these are set so that it's constructed in a similar way, but the vertices have UV values that allow for wrapping, and this was done by hand. The pyramid is very similar to the cube, just with triangle faces, so I had to get a UV value between two far points for some of these, and to get the normal I actually had to perform a bit of calculation to calculate the face normal, and this was using a cross product of two vectors that were extracted from each of the faces. The normals, of course, help with the lighting, the final model lighting. And then for the sphere, it's a little bit more complicated. So this algorithm works in mainly two parts. So first, all of the vertices are walked through. So it's a UV sphere, which means each of the faces are basically squares represented as two triangles with horizontal and vertical bands all around the sphere. So starting at the bottom, I travel through each kind of horizontal circle on the sphere and assign the vertices using a rotation around the center. And since the radius of the circle is just one unit, I can use the position as a normal, as the normal vector value, since the position of the point relative to the 0, 0, 0 vertex is the same as the normal for that point. And then I go through the indices. So I, instead of going by vertices, I go by whole kind of bands of triangles. So getting back to my DX main scene. So after the loading of the models, the camera matrices are initialized as normal. And in the update scene, I have a block of my own transformations for the world matrices of some of the objects. So this is what allows the dragon to kind of circle in the sky, and my primitive shapes to orbit around that portal object model. And then as far as the draw scene, that's also fairly simple. I start by just the usual operation of clearing the buffer and the depth stencil. I update the world matrices for the objects that change position in the scene. And then using the lit texture shader, I render all of the graphic objects that use that shader. And then I stage the unlit texture shader for rendering the skybox, because you don't want the light affecting the skybox. And then finally, for just to demo my lit color shader, I stage that and render the sphere that's in the scene using that. And then the swap chain is presented, and the whole cycle repeats. So I'm going to walk through my graphic objects that I've settled on. So I have 3 classes that I use, other than just the base class that these are inheriting from. So I have the texture light, color light, and texture graphic objects. So firstly, if we jump to the texture light object, this is pretty simple. I have a custom struct for instance data for each of the meshes that might be in my graphic object. So that includes a texture and the Phong model lighting settings. I have a constructor that takes in a shader and a model pointer. And then I hold on to that shader, an array of the material objects, and a world matrix for my graphic object. So the graphic object constructor simply sets the model, shader, and world properties, and then creates a material array that stores this data per mesh. And then I have my 2 setters for assigning values per mesh, or this would be the one that assigns per mesh based on the mesh number, or for all of the meshes. And then to actually render the scene, I go through all of the meshes and perform the setting to context, sending the world and material data through the shader through to the constant buffers, and then rendering the model. So if we take a look at the color light shader, it's very similar, except instead of relying on the material struct that holds all the necessary data, I simply have a vector that holds all of my mesh colors. And then in the constructor, I create the new vector, since the vector array of mesh colors. And then since I don't need an object, a specific object for the values in that array, I just kind of initialize them to a vector of 0. Then I have my 2 setters for per mesh settings, or for all meshes, and then a render method that's similar to what you saw in the texture object here. And then the texture graphic object is again very similar. I'm not going to go through all of this again, because a lot of these features are shared with the other 2 graphic objects. But the reason I kept this one around, even though it doesn't respond to light data, is that you occasionally want to render things without reflectivity or any or material that doesn't react to light. And in the case of my scene, the skybox is rendered using this shader, this graphic object, which relies on the unlit shader texture shader. So if we jump to my shader objects, I can walk through some of those. So again, a base shader and a shader that corresponds to each of these graphic objects. So let's look at the texture shader. So the shader texture light shader starts out with, you'll see a lot of structs that hold specific data for materials, for the Fung model, directional light settings, point light, and spotlight settings. And these are all organized into the struct, which is one of the constant buffers for my shader texture light shader. And then I also have two constant buffers, one for camera matrices and one for world data. So in total, 3 constant buffers for this shader. So the initializer kind of takes care of the setup of creating the input layout data, buffer descriptors for all the constant buffers. So I have one for the matrices, one for the light parameters, and one for the world and material data. I have a function for sending the chem matrices, so this updates the constant buffer for those. Same with the light parameters and the world and material. And then I have setters for all of my light data, so directional, point, and spotlights. And then, of course, there's the set to context, which sets the vertex shader and pixel shader constant buffers to context, as well as the input layout and the shader itself. And just to quickly glance over at the actual shader file, here's the vertex shader. So it passes through the position text coordinate and normal data. And then in the pixel shader, all of that is combined with the lighting data. So first, the Fung model is computed for each of the point lights, spotlights, and directional lights. So in this case, I can have multiple point and spotlights. So that goes through a loop. That's one of the parameters, and the light constant buffers is how many of each of these lights we have. And then this is combined with the texture color to give the final color. So the shader color light is very similar, follows almost the exact same structure as the texture light shader, except that no texture is used, and instead simply plain color data is used to render the object. But this will look very similar to the texture light shader. And then finally, the simplest of these is the texture shader, and that simply has 2 constant buffers for the view and projection data and the world data. And then a simple initializer that takes care of those, setting up those constant buffers and the input layout. And then methods for sending that data and setting to context. So I'm going to jump over to my skybox class, which is its own standalone kind of almost graphic object. So this starts out with a device context, texture, shader, and a default value for how big the the skybox should be. And then similar to my to the code for creating my boxes, this follows the same structure but with normals pointing inward and the UV values kind of assigned to follow my texture. But just like a graphic object, I have my set to context followed by sending the world data and rendering routine that happens when you call the render method. And then the last kind of interesting bit of code that I have is the terrain model class, and this takes in height map as well as some parameters, so that would be length, max height, and Y translation, as well as the UV repeat parameters. And all of these have default values, so if I go over to my header, you'll see if you leave those blank, it'll kind of give you a baseline to start with. So first, the map is the height map is parsed, and then just like the sphere, this works in two parts. So first, the vertices are generated. So as you can see by my little diagram here, it works row by row. So each iteration kind of moves through one row and then jumps down to the next row and does this and keeps repeating this until all vertices are assigned position values. And in this routine, the UV coordinates for the texture data are set as well. Then there's the method for, or the routine for generating the normals for these vertices. So starting at the first field vertex, which is one of the ones that doesn't border the edge, I basically go around, and just like in the pyramid, use the cross product to kind of get a face normal for each of the surrounding triangles. So each triangle surrounding a point gets calculated here, the normal. And then these are all averaged out to get the normal for that vertex. And then as a final step, the indices are generated. So that sums up most of my API. I'll play that scene again just to refresh your memory on what all of this looks like when put together. Okay, thank you.